So I set you up yesterday for the question that we needed to be thinking about today. First, we were dealing with where is the variable, right? So if the variable is in the base, so if the base is the variable, we use the power rule for polynomials. Right, so an example of that would be x squared, and that becomes in derivative 2x. And then yesterday, we learned if the power is the variable, and that's what's changing, then we learned that we needed to use the exponential rule. And so that was where the 2 and the x are in reverse positions. And then we learned yesterday that that became 2 to the x times the natural log of 2 times the chain rule of 1. So we've covered when the base is a variable. We've covered when, I can't spell, the power is a variable. So that leaves us to the last question, which is going to finish up the end of chapter 4. And the last question is, well, what if both are variables? Okay, if both the base and the power have a variable in them. So that's the final thing we need to deal with. If both the base and the power are variable, then we need logs. And so logs are going to come into play to help us out with that particular situation. So we've almost covered everything for derivatives we need to know. We've covered how to do it for constants, how to do it for products, how to do it for quotients, how to do it for polynomials, how to do it for trig and inverse trig, exponentials, and now our last one is how to do it for logarithms. So here's the rule that you need for logs. Log derivatives. If y equals the log of anything, and that log has a base of b, then again, this is something you need to memorize, just like you memorized the trig rules, you memorized the inverse trig rules, bless you, you memorized the exponential rule. The derivative for logarithms, y prime, starts with the fraction, bless you again, 1 over a. So that's whatever's in the parentheses. If you've got a log, whatever is in the parentheses is going to be 1 over a. Followed by another, you know how the exponential had times the natural log of the base? And this is times 1 over the natural log of the base. And finally, a prime. So it's similar to exponentials, where exponentials started with the thing that was itself times the natural log of the base times the chain rule. This is logarithms, and so they're fractions. So it's 1 over that quantity times 1 over the natural log of the base times a prime. So let's just practice how that goes. It's a lot of plug and chug again. All right, so let's just go through a series of examples where I'm going to give you the function and then we'll find the derivative using this new logarithm rule, which I'll try and keep on the screen here. So suppose we have the log base of 4 of the quantity 3x. So its derivative would follow the logarithm rule. So y prime would be 1 over, okay, what would be the base of the first fraction? Or the denominator there. 1 over what? 3x. Times 1 over the natural log of what number? 4. Times the chain rule on what was in the parentheses, which is what? 3. So now we need to simplify and clean this up. So my chain rule of 3 is going to reduce my original 3. My natural log of 4 is a composite number, and 4 is the number 2 squared. And so I need to remember that my rules are I need to deal with pulling that 2 out to the front. So in its correct form, the derivative will be 1 over 2x ln 2. The 2 that's out in front comes from the power on the 2 squared that I'm able to pull out to the front of my logarithm. Okay, everybody follow that, or does somebody need to see that again? Okay, let's try another one. Okay, if y is defined as the log of 3x plus 1, and then we need to find its derivative. So y prime equals 1 over the quantity of 3x plus 1 times 1 over the natural log of what number? 10. This is a common log. Times the chain rule, which is 3 again. Now this time, my 3 chain rule does not cancel out with the 3 in the 3x plus 1. Those are not the same quantities, so they don't simplify. The 10 can't be simplified because it's not a power number. And so there's not a whole lot I can do to this other than write 3 as my numerator, 3x plus 1, and the ln of 10. So that's not nearly as nice and clean as the other one was because nothing simplified. All right, let's try another one. How about the natural log of the square root of 5x? It follows this, it's a logarithm, so it's going to follow the same rule, dy dx, just so we're used to using different notation. So 1 over the square root of 5x, because that's what was in the quantity of my log, 1 over the natural log of what base? E, and then times the chain rule on the square root of 5x. So that's going to be 1/2 times the quantity 5x, which now has a new power that reduced to negative 1/2. And that also needs its own chain rule to multiply by 5. So now we do have some cleaning up to do. I'd like to start with this part and clean that up. So for now, I'm not going to really touch the rest. I'm going to have 1/2, and I'm going to have 1 over the square root of 5x, and then I'll still have my times 5. So working on not having a negative exponent and not having a rational exponent. So now the natural log of e always has a value of 1. We all know that. We have 2 square root 5x's that can multiply together, which is going to make just a plain 1 over 5x for me. I still have my 1/2, and I still have my 5 chain rule. So at this point, the 5 chain rule can reduce the 5 that came from when I ended up combining the square roots. I end up with a very simple 1 over the quantity 2x as my derivative, which is probably not what you would have expected just by looking at the original problem in its original form. Bless you. Okay, any questions on that? All right, so now we're ready to answer the question, what do you do if you have a variable in both the base and the power? And so let's write it this way. If y equals a to the b, where a and b both contain x. So if that is a situation, a is something that has x in it, and the power b is something that has x in it also. Then y prime is found by first applying a log, natural. And so we're first going to apply ln to both sides. And second, apply the product rule. So what does that look like? Let me just... All right, first, we're going to apply an ln on both sides. We're not going to do calculus. We're going to do logs first, a natural log. So that will become ln around the quantity y on the left and ln around the quantity a to the b on the right. The properties of logs allow you to do what with that b value? Bring it to the front. So this becomes ln y equals b times ln a. Then I'm going to apply the rules for the product rule. Notice I haven't done any calculus yet. I've only done ham stuff so far. My ham stuff has been to apply a log on both sides and then pull the power to the front. Now you're going to apply the rules for calculus. And so you're going to use the derivative rule we just used in conjunction with the product rule. And so now we're ready to differentiate. Both sides. So that's going to give me 1 over y. And the rule is then 1 over the natural log of the base, which was e. Followed by the chain rule of the derivative of what's in the parentheses. And what's the derivative of what's in the parentheses? And don't say 1. Because the only variable that has a derivative of 1 is x. Okay? The derivative of this is either you can write y prime or you can write dy dx. It doesn't matter to me. On the other side, we're going to need the product rule. So my product rule says, okay, start with ln a and multiply it by the derivative of b. What's the derivative of b? And don't say 1. db dx or b prime. Plus b times the derivative of natural log of a. And that rule was 1 over a times 1 over natural log e times dA dx, the derivative of that. Now all the natural log of e's are going to be 1. So that's gone, that's gone. So we're left with 1 over y dy dx ln of a times db dx and b over a times dA dx. I know those are a lot of letters, but what am I trying to find? What is the purpose? I was given y equals. What am I trying to find for this whole thing? The derivative of y. Where is the derivative of y in what I've got left? It's right here. That's what I'm looking for. So how do I get that by itself? Multiply both sides by y. And so the dy dx will be y itself times all the rest of that stuff. ln A dB dx plus b over a times dA dx. Now, that's doing it with a bunch of letters. Let's actually do it with a real problem. This is called, this process, where should I write that? Okay, all of this is called logarithmic differentiation. I like the name because it just tells you, it's the instructions of what to do. Logarithmic differentiation. So logarithmic means start with doing logarithms. And then the second part is do the derivatives using the product rule and the other rules that you learned. You only do this, or the best time to do this is when both the base and the power have an exponent. So let's do a problem where both of them have an exponent. Let's say that y is x to the x squared. X to the x squared. So this would be a perfect example of when you would want to use logarithmic differentiation because a variable is both in the base value and it's in the exponent value. So we're going to do logarithmic differentiation, which means we're going to apply ln. And we do that on both sides of the problem. So ln gets applied parentheses to y, and ln gets applied parentheses to x to the x squared. My next move is to move that x squared down to the front times ln x. Remember, none of this is calculus. This is ham, it's pre-calculus stuff. Then, once you've completed that, then the second step is to apply the derivatives. This is the differentiation part, so we're going to apply the derivative rules. On the left side, I will need the derivative rules for how to take the derivative of the natural log. On the right side, I'll need the product rule. So on the left side, I need the derivative rule, which is 1 over y times 1 over ln e times dy dx. The left side's always the same. On the right side, I'll need the product rule. So I'm going to need b times a prime plus a times b prime. So my product rule says have the ln of x go first, and then multiply that times a prime, which is 2x. And the second half of it says, okay, now start with a, which is x squared, and multiply that by b prime. And the rule for b prime is the new natural log rule we just learned. So 1 over x times 1 over ln e times the derivative of x, which is the only time the derivative is 1. So now go ahead and clean up your natural logs of e, which you won't need anymore. So we're going to have 1 over y times dy dx on the left. And we'll be left with, I'm going to put my 2x in front of my ln x. I just prefer to have the polynomial part in front and the natural log in the back. And then after the addition sign, how does that simplify? What am I left with? X. And do you notice that these two things now have something in common with each other? What is it? X. So I would encourage you to recognize that and factor that out. So take out an x. That would leave you with 2 ln x plus 1. And my last move is to get dy dx isolated by multiplying the y on both sides. So my dy dx is going to be y times x 2 ln x plus 1. And what was y to begin with? Okay, so replace that y with what it was. So your final answer would be x to the x squared times another x times the quantity 2 ln of x plus 1. That middle x there that's sitting there, what's its power? Okay, and what's the rule that I could do with the first x to the x squared and then the second x to the first? What can I do with those two powers? I can add them, right. And so another way to write this same answer would be to not have that x there at all and have plus 1. And that would be fine. You might see it written like that. So this logarithmic differentiation is awesome in that situation where you have a variable in both. I'm going to show you one other example of when logarithmic differentiation is great. And I'm going to propose to you that logarithmic differentiation gets you out of the quotient rule. If you're not a fan of the quotient rule, then I'm going to show you how logarithmic differentiation can get you out of it. You don't have to use it. Sometimes the quotient rule is slick and great and it works out beautifully. Other times the quotient rule just gives you this mess. And so I'm hopefully going to prove to you that logarithmic differentiation might be actually a cleaner way of getting the answer. All right, so our example would be this. Y equals x plus 5 over x cos x. Now you could totally use the quotient rule for this. But be aware, when you get to the b prime part of the quotient rule, what are you going to need to remember to use while you're using the quotient rule? The product rule. So you're going to have the product rule nested in the quotient rule when you get to the b prime part. So that's fine if you want to do it that way. As long as you're careful, you'll get the right answer. But let's try it with logarithmic differentiation and see if that might be a little bit of a cleaner way to do it. And so we apply natural log. On both sides, so we'll have the natural log of y is the natural log of x plus 5 over the quantity x cos x. Now there's no power to pull to the front, but there are some other rules and properties of logarithms that I can use. When a logarithm has a division problem inside, do you remember what you could do with that? You could subtract. And so this would become the logarithm of x plus 5 minus the logarithm of x and minus again the logarithm of cos x. When both of those terms are in the denominator, they both would be subtracted because they're both part of the division. If they happen to have two things in the numerator, then you add them. So that's not so bad. Then we apply the derivatives. And because each piece of these has an ln, they're all going to be 1 over, and then 1 over, and then 1 over. So the natural log of y has the derivative 1 over y times 1 over ln e times dy dx. The natural log of x plus 5 has the derivative 1 over x plus 5 times 1 over ln e times 1, because the chain rule happens to be 1. Minus the natural log of x is 1 over x times 1 over the natural log of e times 1 again. And my last minus is 1 over cos x times 1 over natural log e. And then the derivative of cosine x, which is negative sine of x. So I was very careful to write out all of my natural log e's right now, but of course all of those natural log of e's are 1. So this problem will simplify into 1 over y dy dx, 1 over x plus 5, minus 1 over x. And then what about the last term? What will that simplify to? I've got a minus 1 over cosine x times a negative sine of x. What will that be? Positive or negative? Positive. And I'm looking for dy dx, so I just need to get it alone by multiplying by y. So dy dx is y times 1 over x plus 5 minus 1 over x plus tan x. And you'll be glad to know you don't need a common denominator. And then you'll want to replace y with what it was defined to be in the first place, which was x plus 5 over x cos x. You don't need to get common denominators. You don't need to simplify. You don't need to distribute. That's it. But would you believe that that's the same answer, the equivalent answer you'd get if you had done the quotient rule? Okay? But this is a lot cleaner of an answer because everything is factored nicely and in fractions nicely. So some of your problems are going to start out straight with just plain logarithms, just plug and chug, and that'll be it if it's just a logarithm. You will use logarithmic differentiation in the situations where you have a variable in both the base and the exponent, and maybe as an alternate to the quotient rule.